Hello friends, today I am going to discuss with you the concept of MODUS, PONENS and MODUS TOLLENS, their validity in natural language arguments. This is Professor Rakesh Kumar Katare of Department of Computer Science at APS University, Rewa, Madhya Pradesh. The validity of modus ponens and modus tollens is discussed in this presentation. Here we are analyzing the variety of conditional as 1. Sufficient condition for the main class, or second, the conditional class as a necessary and sufficient condition for the main class. What is conditional? If P and Q are any two statements oblique proposition, then the statement P implies Q, which is read as if P then Q, is called a conditional statement, conditional proposition or implication. The statement P is called the antecedent or hypothesis and Q the consequent or conclusion. Truth table for P implication Q is presented here. P and Q are two statements. The possibility of P is like this, the possibility of Q is like this. P implication Q is this. What we found here is TT is T, FF is T, FT is T, TF is F. TT is T. Example, if x square is equal to 0, then x is equal to 0. If P is x square is equal to 0 and Q is x is equal to 0, then P is true, Q is true, then this statement is true. FF is equal to T. If x square is not equal to 0, then x is not equal to 0. Here P is equal to x square is not equal to 0 and Q is equal to x is not equal to 0, then the statement if x square is not equal to 0, then x is not equal to 0 is true. So these two things I have already proved here. Now Ft is equal to T, Tf is equal to F. Why? These two statements or validity can be proved by using the method proof by contradiction. Proof by contradiction. First, if x plus x is equal to x, then x is equal to 0. Assume x plus x is equal to x and x is not equal to 0. Then what does it means? Then 2x is equal to x, and since x is not equal to 0, we can divide both sides by x to get 2 is equal to 1, which is a contradiction. Our assumption that the implication if x is plus x is equal to x, then x is not equal to 0 is false. It itself false. Therefore, the original implication is proved to be true. Same way, it is identically true for multiplication. If x into x is equal to x, then x is equal to 1. Second, if x square is equal to 0, then x is equal to 0. Let A, if x is greater than 0, then x square is greater than 0. B, if x is less than 0, then x square is greater than 0. C, if x is not equal to 0, then x square is also not equal to 0. Now we see that until unless consequent is not true, then the statement is not true. It means that ft is t. The truth table of the four propositions conditional, converse, contrapositive and inverse is as follows. P and Q are any two statements. P, Q, possibilities of P, possibilities of Q, P implication Q, Q implication P, not P implication not Q, and not Q implication not P. P implication Q is conditional. Q implication P is converse of conditional. Not P implication not Q is inverse of conditional. Not Q implication not P is contrapositive of conditional. So we found from this table that P implication Q is biequivalence of not Q implication not P. Q implication P is biequivalence of not P implication not Q. If P implication Q is an implication, then the converse of P implication Q is the implication Q implication P. The contrapositive of P implication Q is the implication of not Q implies not P, and the inverse of P implication is not P implies not Q. Example: if in any triangle ABC angle B is 90 degree, then BA square plus BC square is equal to AC square. This is Pythagoras theorem when angle B is 90 degree. Now let us take an example. If BA square plus BC square is not equal to AC square, then angle B will not be equal to 90 degree. So equation 1 or statement 1 and statement 2 are contrapositive to each other. Rule of inference. The main function of logic is to provide rules of inference or principle of reasoning. Second, the theory associated with such rules is known as inference theory because it is concerned with the inferring of a conclusion from certain premises. Third, premises are the statements which are assumed to be true. Only then we can expect the conclusion to be true. What is modus ponens or law of detachment? Modus ponens is P and P implication Q implies Q is a logical truth or a tautology. Means the basis of modus ponens is a tautology. Tautology means all T must come here. So this is modus ponens. P and Q are two statements, not P, not Q. P implication Q, P and P implication Q, P and P implication Q implies Q is modus ponens. So this is tautology. Same way, not Q and P implication Q implies not P is modus tollens, which is also a tautology, which we can represent like this. Modus ponens can be written as if P and if P then Q, affirming the antecedent. P is antecedent, so affirming the antecedent. Modus tollens, if not Q and if P then Q, then not P, denying the consequent. Not Q is not is consequent, so we are denying the consequent here. Same way, we are affirming the antecedent here as P. So, modus ponens is mode that affirms, affirming the antecedent. Second, if both an implication and its hypothesis or antecedent are known to be true, then the conclusion of the implication is also true. Or, on the other hand, we can say that the above argument is valid on the assumption that its premises are true, its conclusion must be true. We can prove like this: P and P implication Q is equal to Q is implies Q. T and T implies Q implies Q. P is T. So one premise I have taken as true. T and T implies Q. T and T implies T, which is equal to T. So Q is T. So the antecedent is true, implication is true, therefore the statement is true. Modus ponens and modus tollens are universally regarded as valid forms of argument. Modus ponens is referred to also as affirming the antecedent and law of detachment. Modus tollens is often referred to as also denying the consequent. Example 1. If it is raining today, then we will go for boating. A. It is raining today. B. We will go for boating. Second, if the sun is shining, then the ground is dry. A. The sun is shining. B. The ground is dry. Modus ponens. 1. If A, then B. Second, A. Third, B. This form of argument is always valid. Modus tollens. If A, then B. Not B, so not A. Every argument having the form of modus tollens is valid. This is simplification. P and Q implies Q. It is below freezing and snows now. It is below freezing now. Modus tollens, mode that denies. Denying the consequent can be represented in this manner. Hypothetical syllogism or transitive rule. P implication Q and Q implication R implies P implication R. Disjunctive syllogism. P or Q and not P implies Q. Dilemma. P or Q and P implication R and Q implication R implies R. Only if clause and if and only if clause. First, if then statements indicate implication, whereas only if clause indicate prerequisite. Second, the conditional statement having an if and only if clause indicate both implication and prerequisite. Third, the conjunction only if is less used than if. So, if we say if there is water, then washing is possible. This English sentence is wrong because water is a prerequisite for washing. Thus, they should have said only if there is water is washing possible. Valid argument. A valid argument is 1. in which the premises support the conclusion completely. More formally, a valid argument has this essential feature. It is necessary that if the premises are true, then the conclusion is true. I have shown here that if the premises are true, then the conclusion is true. So this is a valid form of statement. According to this definition of valid argument, modus ponens, which I have shown just before, and modus tollens, which I have shown, guarantee a true conclusion provided the premises are true. Modus ponens and modus tollens are usually regarded as valid forms of argument on the ground that the antecedent is a sufficient condition for the consequent. Sufficient necessary relationship between the components of conditional. The form if A then C, where A and C are variables of the statements. A is the antecedent of the conditional and marks a sufficient condition for C, the consequent of the conditional. So A and C are the components of the if A then C. Similarly, the consequent C marks a necessary condition for the antecedent. These two forms are very important for the sufficient necessary relationship. This relationship is that A is sufficient for C and that C is necessary for A. A is sufficient condition for C, affirming the antecedent, is always regarded as a valid form of argument. Similarly, C is a necessary condition for A. The conclusion denying the antecedent necessarily follows the premise denying the consequent. So, denying the consequent is always regarded as another valid form of argument. Modus tollens empty allows us to infer the negation of the antecedent of the conditional statement, i.e. not A. Not B and A implication B implies not A. To see the validity of such inferences, assume towards contradiction that A is true given the two premises if A then B and not B are true. Then by applying MP to A and if A then B, we can derive B. This is a contradiction and thus A is false, i.e. not A. This is modus tollens, not B and A implication B implies not A. A is false. We can say that A is F. Not B and F implies B implies not F. Because A is F, therefore I have just replaced A by F here. Let B is true. Then I will replace B by T in modus tollens. Then what I will write now, not T and F implies T implies T. So this become T, T and T. Not T become F, not T become F, F implies T is T, F and T is F, F implies T is T. So when B is T, then MT is true. MT means modus tollens is true. Now let us take let B is equal to F. Not F and F implies not F. So F implies F. Let B is equal to F, not F, and F implies not F. So not F is T, F implies F is T, not F is T. So everything is T. So this is T, T implies T is T. So A is false. It is proved because I have taken A as false and I found that modus tollens is true in both the cases. Now let us assume A is true. A is true as I have given before in our example. Here, to see the validity of such inferences, assume towards contradiction that A is true. Given the two premises, if A then B and not B are true, then applying MP to A, and if A then B, we can derive B. This is a contradiction, thus A is false. So let if A is true, then A implication B and not B is A is T. I have replaced A by T, implication B and not B. T and not B. Not B is T. T implies B. T implies B is T only when B is T, otherwise not. So this T implies B is T and not B. Now since B is equal to T, therefore not B is equal to F. So T and not B is T and F, which is F. This F, B is equal to F, a contradiction. Now apply modus ponens to A. A and A implication B, which is B, implies B. T and T implies F implies F. So T and F implies F. F implies F, which is T. Hence A is false, not A. Therefore when I take A as T, this is a contradiction. This is a contradiction which is not correct. So A is always false. Now we will again analyzing the conditional. Are some modus ponens arguments deductively invalid? There are many common arguments used daily in everyday reasoning that have the form modus ponens but are not deductively valid. Classification of conditional statements on the invalidity of modus ponens. Walton's view. Walton divides conditions into three types: the absolute conditional, the probabilistic conditional, the abductive conditional. The feasible and plausibilistic. In cases that the first premise is the probabilistic or abductive conditional, he suggests modus ponens is deductively invalid. But he also admits that modus ponens is valid in the case of an absolute conditional. Denying the antecedent dA and affirming the consequent AC are regarded as invalid forms. Denying the antecedent, a common fallacy. A fallacy is an error in reasoning that results in an invalid argument. Affirming the consequent AC. Only if there is water is washing possible. My uncle's town is famous for washing, therefore there must be water. This is an example of affirming the consequent. Now, denying the antecedent. Denying the antecedent dA. Only if there is water is washing possible. There is almost no water in desert, therefore washing is impossible there. In these examples, water is a necessary condition for washing, and the conclusion are necessarily derived from the premises. Finally, I get into the cases of necessary and sufficient condition. The following geometric arguments are typical instances of arguments which have a biconditional as the major premise. Affirming the consequent AC. If and only if two straight lines run parallel with each other, their corresponding angles are equal. Angle A and B are equal. Therefore, L and M run parallel with each other. L and M are two parallel lines. I have drawn this. Angle A and B are equal. So this is the example of affirming the consequent. Denying the antecedent dA. If and only if two straight lines run parallel with each other, their corresponding angles are equal. Straight lines L and M don't run parallel with each other, therefore angle A and B are not equal. These two examples show that AC and DA are valid in the case that the antecedent is a necessary and sufficient condition for consequent. Now we have more examples here. Test the validity of the following arguments. If two sides of a triangle are equal, then the opposite angles are equal. Another way, two sides of a triangle are not equal, therefore the opposite angles are not equal. These are also the examples of accepting the consequent, affirming the consequent, and denying the antecedent. The following table summarizes the validity and invalidity of the modus ponens and modus tollens. Condition: sufficient, necessary, necessary and sufficient. Modus ponens, modus tollens. Affirming the antecedent, affirming the consequent, denying the antecedent, denying the consequent. So sufficient, for sufficient condition, modus ponens gives a valid conclusion. Modus tollens DC is valid. Necessary, modus ponens AC is valid, and DA valid in modus tollens. Necessary and sufficient for modus tollens, all are valid. MP includes not only A but also AC, and modus tollens MT includes not only DC but also DA. The antecedent is a necessary or necessary and sufficient condition for the consequent. This is important. This is very important. In cases of a necessary conditional, AA and DC are invalid and cannot prove the conclusion. On the contrary, AC and DA can be used to establish a connection with certainly because they are valid. This is bibliography. Rule of inference, tautological form, name. So, simplification, rule of inference, tautological form. Addition, rule of inference, tautological form. Disjunctive syllogism, rule of inference, tautological form. Modus ponens, modus tollens, hypothetical syllogism, dilemma. Basically, this presentation is prepared from this reference. Thanks.